Okay, so now we move on to the topic of time series. So the key learning objective here is to understand how to model when the residuals are correlated over a time sequence. So the key distinction here is this correlated over time sequence. We've discussed in some detail how to model when the residuals are uncorrelated, but now we're going to look at the situation where the residuals are correlated, but specifically they're correlated over a time sequence. So when data are collected in a series over time, we call this a time series. The standard methods require that the data are collected at equally spaced time points, whatever that might be. It could be hourly, daily, monthly, or yearly. The key difference from simple linear models is the assumption that errors are independent, we know is not valid. The simplest case is what we call autocorrelation. In other words, the correlation of the errors from yt and yt plus k, where t plus k means it's observed k units later than t. The correlation is rho, where rho is some parameter to the power of k. So you will see that this says that errors that are close together in time have a stronger correlation. So rho is always between -1 and +1. In fact, usually it's between 0 and +1. It's quite rare we would have a negative autocorrelation. But a positive one would mean if, for example, rho is close to 1, that means that the correlations only die away very slowly as k goes up. But if, for example, rho was a half, that would mean 1 unit apart would have a correlation of a half, 2 units apart would have a correlation of a quarter, 3 units apart would have a correlation of an eighth, and so on. So you can see that unless rho is large, these effects will die away. The key issue is, if we have autocorrelation, then each data point doesn't add as much information as we would expect using the statistical methods which assume independent error. So our effective sample size will go down. So the obvious test here is to test whether rho is equal to 0. Right? That's the key point. If rho is 0, then we don't need to worry about time series. We can go back to the methods we've already examined. So this is another form of diagnostic check that we haven't yet looked at. This test for autocorrelation is called the Durbin-Watson test, and it's wise if our data has an obvious ordering. So for example, the Longley data set that we looked at before, let's have a look at what we get there. So remember, this is not checking actually that the y's are correlated, it's checking that the residuals are correlated. So in this particular case, remember, we can explain a lot of the variability in the Longley data set. So it's going to be much more sensitive to correlation of the residuals than the original raw data. So we don't need to worry about the top half. This is just the standard analysis with these 3 covariates that we found earlier were useful, x3, x4, and x6. So that we then get that residual plot at the bottom, and then the key part is the part in the bottom left-hand corner. This is the Durbin-Watson test. It tells us that value of the statistic is 1.46. We only have 16 observations. The estimated autocorrelation is 0.13, and the significance level is very close to 5%. But an autocorrelation of 0.13 is relatively small. That doesn't really have a big impact on our estimation processes or our tests. Okay, so this situation where rho is not equal to 0 requires a relatively simple generalization of the linear models we've been discussing. As I said, autocorrelation means that we have less information than we think, i.e. the effective size is smaller. So what other types of time series model might we be thinking about? Well, one issue is a seasonal effect. That means we have an independent variable that denotes which season. So clearly this could literally be the seasons of spring, summer, autumn, and winter, or it could be months of the year, or it could be days of the week. So if this is just a particular factor, we can include it in the linear models we already know how to handle if we know the length of the cycle. So as I said, seasons are not necessarily seasons in the usual sense of the word, but the stages of any cycle. So finding the length of the cycle may be an important part of the analysis for some data sets. Special cases are where the seasonal pattern follows a sinusoidal curve. So for example, anything that's linked to the moon or the sun, so a lunar or solar pattern. So one example of this is tide heights. So tide heights actually have two competing elements. One is the sun's effect and one is the moon's effect. So we can identify those patterns and see how those affect our cycle time. So this is usually not too hard if we plot the data. It's usually relatively easy to identify the length of the cycle and what sort of cyclical pattern we have if that cyclical pattern has a large effect. So the next stage of sophistication in time series models is differencing, moving averages, and autoregressive models. So the basic idea of these generalizations, which we usually consider together, is that by using differences either of the observed y, that's what we call an autoregressive model, or looking at differences of the residual errors, which is what we call moving averages, and then possibly after initial differencing to remove trends, we can get a simple linear model. So these elements together are called ARIMA models, which is short for autoregressive integrated moving average. So this is a bit complicated, so let's look at the simpler part. So an autoregressive model means that any forecasts are based on a linear combination of the previous values. The moving average one, the forecasts are based on a linear combination of the previous errors, meaning a linear combination of the residuals. So these are the two primary ones, plus of course the seasonal effect. So ARIMA models combine differencing, AR, and MA. Okay, so what does differencing actually mean? So differencing would mean that instead of looking at YT, we look at the change between YT minus 1 and YT. So you can think about it that this will help us to remove trends. So this, by calculating the difference between an observation and the one before it, we need to remove trends because the standard methods assume that the mean and the variance are stable over time, which is what we call stationarity. In time series context, stable variance, we already said, was a key assumption in all of these models. So let's take a very simple example. Let's say we started out with a simple linear trend in time, so that YT can be actually written as A plus BT plus an error term. Then if we do a differencing of YT and YT minus 1, the A's cancel out and the B's partially cancel out in that the earlier term would be B times T minus 1, so the differencing gives us a B. So the trend slope B becomes a constant in this revised version, right? So we would have then that the differences, the first differences between YT and YT minus 1 should show a constant plus an error term if indeed the original model was a simple linear trend. If we do differencing a second time, so we look at the difference of the differencing, then the B also disappears, and so we get just a random error term. So this is one way we can check, is by doing differencing and seeing whether trends disappear or whether constants disappear, so that we end up with just a random error term. So general ARIMA models in general are hard to identify, but special cases are easier. So if it's a pure moving average with k terms, then the autocorrelation function will be 0 after the kth term. So this is just meaning the autocorrelation of YT with YT minus k. If we have a pure autoregressive model with k terms, what we call the partial autocorrelation function will be 0 after the kth term, where the partial autocorrelation function is the sample correlation between yt and yt minus k after first removing the difference of the intervening y on both variables by using linear regression. So in other words, the partial autocorrelation function is the autocorrelation of the residuals from the regressions. Now we don't have to do all those calculations. The statistical package will do this for us, and it will plot both the autocorrelation function and the partial autocorrelation function, so we can try and identify whether there is a pattern. So this is our first example. This is looking at monthly ozone concentrations. So if we look at the plot up at the top, you can see there does appear to be some sort of a pattern here. There does appear to be a downward trend. So that downward trend means that probably we'd need to do differencing. And then we have our diagnostics below. We have the autocorrelation function on the left and the partial autocorrelation on the right. So if you look at the right hand side, you can see the first partial autocorrelation is quite large. So that would imply that there is a trend here. And you can see there is a pattern in both the partial and autocorrelation functions. There's a trend, there's some seasonality in there. So for example, in the autocorrelation function, you can see that the autocorrelation with a lag of 12 is relatively large and positive, and at 24 is relatively large and positive. So that implies that there is some sort of seasonality pattern across the months of the year, and so we would want to remove that seasonality pattern and see then what was left. So that's showing us our strong seasonal pattern, and indeed if you look at it more carefully up above, you can see that if you look at successive peaks or successive troughs, there is a gap of around 12 units, right? So this is monthly data. So we can see that there is a seasonality pattern within a year. Okay, this second example, if you look at the top, this is not such a nice even pattern, but this is showing us that there is a consistent pattern in the sense that there are the time gap between successive troughs and peaks is relatively stable. So this is data on yearly data. This is actually the number of lynx. So lynx is a wildcat. So this is data on the number of cats that were caught by the trappers in Canada. And there is a consistent pattern, a consistent cycle of about 9.5 years. So this can be seen as the number of cats goes up to a peak, and then it drops down again, and it goes up again and down again. So the primary issue in this situation was not the trappers themselves, but there was things happening in the ecology of Canada that meant that the population size kept going up and down in a relatively stable cycle, although the peak you can see is not that consistent. So if we look at the diagnostic plots, again, you can see, particularly in the autocorrelation, the very strong seasonal pattern with a cycle time of around 9.5 years. So you can see there's a peak at about 9.5. There's another peak at about 19. And in the autocorrelation function, you can see the first and the second autocorrelations are quite large. Okay, so that's showing us the pattern there. This is a pattern for passenger numbers. So if you look in the top left-hand corner, you can see that the passenger numbers do go up over time, but you can see that the variability is changing over time. The variability is increasing. So not only is the average count going up, but the variability is going up. So this turns out to be a situation where often A log transform will be helpful. So this is an approximate way to turn count data back into something that's a little bit more like normally distributed. So if you look at the top right hand side, you can see the pattern for the log of the number of passengers. Here you can see we have much closer to a stable pattern, that there appears to be a linear trend, and there appears to be that the variance is relatively stable. And we can also see that there is a consistent cycle time here. Again, this is monthly data. If you look at the autocorrelation and partial autocorrelation, you can see the partial autocorrelation shows a very strong peak. So there's a very strong first partial autocorrelation, meaning there's a very strong trend effect, plus the effect at 13. So you can see this is basically saying we have a strong seasonality pattern and a strong trend pattern. And they are very nice. Once we look at the log pattern, you can see that the pattern is indeed simpler once we've converted to the log scale. And so we can easily model the primary effects in this one as well. So this one's a little bit different. This one is carbon dioxide. But again here, this one is not so different to the log passenger ones in the sense that we can see a very strong seasonal pattern. And we can also see a very strong trend. So again, we can see this showing up in the sense of the very strong first order partial autocorrelation, meaning a very strong trend. And we can also see the very strong trend in both the autocorrelation and partial autocorrelation, indicating that there is a seasonal effect that we need to remove. Okay, so that brings us to the end of the section on time series.